Okay, so let's get started with the basics of NMR, starting with ethanol. So if we look at ethanol, the first thing I like to usually do when looking at NMRs is just to get an idea of what we're working with here. So we have one singlet, one quartet, and one triplet. So the way we can tell what these are is this has three. There's three total uh, readings here. On this one, there are four total right here, and this one is just one. So the way we can separate specifically this one from the four is that it should have some sort of symmetry usually. If it's not or if it is part of it. So if we look at these two readings right here, this one compared to this one, they're pretty close. Same with these two. That's coupling. So let's also look a little bit at integration here. So the nice thing is that the integration is already done on these ones. Usually integration will be, in a little space down here. It'll give you some numbers. What you'll end up doing is taking those numbers and you'll find the lowest one and divide the rest of them by that. That will give you your baseline for integration. So let's really get to solving this one real quick. So when I come to an IR or an NMR graph, usually what I'll do is I'll start with the hydrogen inefficiency. Ethanol, they don't give you the formula on this, but ethanol is C2H5OH. So to do this, what we're going to do is we'll take 2 times the number of carbons, which would in this case be 2 again, plus 2, subtract the amount of hydrogens. In this case, it would be 6. So you might wonder why it's 6 instead of 5. There's 5 carbons or 5 hydrogens here, 5 hydrogens here for a total of 6. You divide that by 2, but we don't really need to do that because we can see that this top part right here is going to be 0, and you can't divide 0 by 2. You're just going to get 0 again. So what that means is that there's no degree of unsaturation. So that means this is free of rings and this is free of double bonds. All right, so the next part that we can work on is start thinking about what these are relating to. So we have our triplet, our quartet, and our singlet. So that would mean that we should have one that has no neighbors or one neighbor in this case because it's attached to an oxygen. So that would be our singlet. So that would probably be our OH group if we had to bet, right? For our quartet, that's going to have 3 hydrogens on a neighboring molecule. So if I had to bet, that's probably going to be our middle carbon that's attached to the oxygen and to the other carbon. The reason we can think this is because we have that CH3 group on the end of this, probably, which is what would account for 4, right? So if we use the N minus 1, we're going to see that 4 minus 1 equals 3. So we have one CH3 group for sure, because that's going to give us that quartet. And then this is a triplet, so we'll use the N minus 1 again, which would be the 3 minus 1, which is equal to 2. So we'll probably have a CH2 group in there. And we have our singlet, which is that's our OH group. We know that because these hydrogens are taken care of, this hydrogen is taken care of. So if I wanted to put this together, right, we have our triplet group and our quartet group are different ppm wise. So if we're assuming that our OH group is indeed that 1H, that means that we would have something where it's OH. Oops. So we'll have our OH group, okay, attached to the carbon that's neighboring the one with 3. So that would mean that's going to be our CH2, right? Because this is neighboring this one. So that's going to be attached to a carbon here. So we have these 2 hydrogens. And that basically just leaves us with our last group with our 3H, or our 3H, our quartet. So we are carbon here, hydrogen here, hydrogen here, and hydrogen here. So let's take a little bit of a look at the grouping for this. So our group that's responsible for this quartet is this one right here. Because if we do the n-1 rule backwards, so it's n+1, that's going to give us 4 proton readings. So let's move down the line a little bit more here. We have our 2 here, again, the n+1 in this case, so that's going to give us 3, which is these ones over here. Well, yeah. And then we have this last little hydrogen here. So this hydrogen is it's further downfield right here because of this oxygen right here. This oxygen is very electronegative. And usually when things are close to electronegative, they're going to be pushed further down, which is also why the carbon that gave off this reading, the one that's neighboring this one, so not this one here, but this carbon is further past this way. But usually a good estimate for where to call it as something else externally influencing it is usually after the 2 ppm mark. So everything this way has something else pulling it downfield usually. Okay, so let's move on to the ethyl acetate. So ethyl acetate is a formula of C4H8 O2. Again, let's start with that hydrogen deficiency. So that's going to be 2 times 4, because there are 4 from the carbons, plus 2, and then minus 8, all divided by 2. So this up here, this is going to be 8, 2, so 2 over 2 is equal to 1. So we have 1 degree of unsaturation here, meaning we most likely have a double bond to something, because it's highly unlikely that we have a ring of 4 carbons in this case. So if we know that, and we have 1 singlet right here, so it's a single bar. We have 1 triplet here, and we have our quartet over here. So this correlates to a carbon that is next to another carbon with a CH3. This singlet is a carbon that is next to nothing, or a carbon that's next to another carbon with no hydrogens attached. So this is most likely the one that's making a double bond if we had to bet here. And then our triplet, this is our CH2. So we know we have to have each of those, right? So let's brainstorm an idea here. So if we want to connect these carbons, so we'll do a carbon to a carbon. Likely we'll have 1 over here with our H's, right? So we get our triple group over here. And the other thing we need to look at is a little bit of the integration. So we have 2H here, 3H, 3H. So think about how many hydrogens those are accounting for. So we also have these oxygen groups. So considering that this one is just past 2, we're most likely going to be closer to an oxygen here. And this one is most definitely close to one of those electronegatives. It could even be close to both of those oxygens. So let's try that out real quick. So if we put an oxygen over here, and we assume there's just a double bond here to this oxygen, because we have to have a double bond somewhere. And it would make sense for it to be with this oxygen, because that would help push this group, which is corresponding to this one, remember, further over to the left here. So we still have 2 more carbons to deal with. We need another CH2 and 1 more CH3, which I think if we do this right, that could work out perfect, right? So we put our hydrogens here, and let's try putting that group over here. So it's going to be a carbon, hydrogen, hydrogen to a hydrogen. Okay, so now we brainstormed a structure. Let's take a look at how many groups there are here of hydrogens. So we have this one right here, because that's to carbon, carbon is to an oxygen. This one right here, because these hydrogens are closer to this oxygen than these ones over here. So that would make this another group right here. Now let's think about, why are these ones so far over here? Well, this carbon right here is making not only 1 bond to an electronegative, but 2, technically 3, because it has a double bond and a single, but it's next to 2 of them. So that's going to push this far over here. That's why it's even past 4 ppm. And if we look at this one right here, this is corresponding to this one. And the reason that it's even over here, even though it's not directly connected, is because it's closer to that. So it's still above 2. Alrighty, now let's look at propanol. So 2-propanol is C3H8O. So if we have, let's start again how we did before with our IHD. So that's going to be 2. And we have our 3 carbons plus 2 minus our 8 hydrogens divided by 2. So we know that this up here is going to be 0, and anything divided, or 0 divided by anything, is still 0. Let's look at our graph that we have here. So we actually should get 3 signals with this. There should be another one somewhere in here that's a singlet, actually. That's because you'll see when we get a little further, I'll explain why. So we have our idea here. We have a, is that 1, 2, 3, 4, 5, 6, 7. So this is a 7. So septet or multiplet, but looks more like a septet. So we have 1 septet. And then we have, this is very clearly a doublet. So we have 1 doublet. Okay. So when we look at this, we know we have to have the septet. We know we have to have a doublet. So a septet indicates that we have 2 CH3 groups. Right, so that could be something like a carbon attached to 2 other carbons with 3 H's on each of them. Okay, so if we run with that, that is 6 of our hydrogens already used up, which is perfect. We know we have an unsaturation degree of 0, so there's no double bonds that we have to worry about. So now we just have 2 hydrogens and an oxygen. Well, if we look at how far downfield this these septets are, that indicates that they're connected to a carbon that is also connected to an electronegative ion, or an ion, but atom. So that's probably that oxygen. So if we just were to leave this oxygen like this, it's not going to be satisfied because it wants to make two bonds, right? So let's say we throw a hydrogen on there. So we only have one more that we need to deal with. We have that, we can throw one there. That way this carbon has 4 bonds. Perfect. So let's look at the grouping here. Remember when we said that we should get a third reading actually. Now the reason we get a third, these two are equivalent, right? Because it's a symmetric molecule. So these ones are equivalent. That's 1. But this hydrogen and this hydrogen are not because of this oxygen right here. That oxygen should produce one here. So this might be a bad graph. So let's look at ibuprofen. Ibuprofen is a great inflammatory and it's commonly used probably by most people almost every day, especially if you're in college. So the formula for ibuprofen is C13, H18, O2. So let's calculate that degree of unsaturation. Our degree of unsaturation is going to be 2 times 13 plus 2 minus 18 divided by 2. So that's going to be 26. Let's see here. So it's going to be 26, 28. So it's going to give us 5 total degrees of unsaturation, meaning that we should have something with, so we have 5, it's going to be possibilities for 5, right? So we can use 2 up by having a ring, an aromatic ring, I should say, and the 3 in there. So we should have something probably about a ring, an aromatic ring. So that would eat up 4 of those total. And then we'd probably just have a double bond if I had to bet. Okay, so looking at this, we'll have 5 doublets. So we know we have 5 doublets. We'll have 1 multiplet, because that looks like a multiplet right there. 1 quartet here. And 1 little singlet over here. Okay, now can't forget that we have 2 oxygens as well. So our oxygens are most likely going to be around these carbons here. So those are the ones we need to be careful of, which is, that's our, one of our doublets, singlet. Okay, so how can we solve this from here? Well, let's start off by making our ring. We have our ring. And if we wanted to tack something on to either end, because we're going to have to make, with the amount of hydrogens we have in the amount of readings we're going to get, some of them are going to have to be equivalent. So we'll probably tack something on in either direction, which would make some of these hydrogens around here equivalent. So we can probably make a group here or here, but let's branch out a little bit more. So let's go this way. Let's take a few carbons off. So we come down here with that. And maybe we'll tack on a methyl group because we have to take care of 18 total hydrogens. So that's a lot. So that's going to make a group here, a group of hydrogens here and here, because we have equivalency up here. We could also have one here, and these two would be equivalent. So let's go the other way off of the molecule. Come down. We'll have another group here. We come up. And this way, we'll have another here. So let's look at the carbons that need bonds here. So we can tack on those last few oxygens. We probably going to need to put one here. So sterically, that would be a better idea. And then we'll tack another one onto this one because we're pretty well set on hydrogens, but we still need one more. So we'll make that the alcohol group. Now, the reason I think we'll have these two oxygens here is because that would line up perfectly with what we need over here. So this singlet is going to be this carbon right here in the center that doesn't have any hydrogens attached, which that works out great for us. Let's go through and figure out what other groups we're going to have hydrogen-wise here, just to make sure we're going to have enough readings. So we have 1, 2, these two are equivalent, 3, 4, 5, 6, 7, 8. These signals we have 1, 2, 3, 4, 5, 6, 7, 8. Okay. So now let's confirm this using what we know about the coupling and why there are certain amounts downfield. So if we look at these ones in here, we have our 2 electronegatives, our oxygens. That's going to force them to come up this way, right? We have our 1 hydrogen here, which is going to be one of these doublets. We have another right here. Actually, right here. Sorry, this is our other doublet. There's another one right there. That's my bad. So that would be hiding out, making this other one, which makes complete sense because we have these 2 oxygens here and here still, pushing it further to the left. And then our singlet. Now, our singlet, why is it so far up here? That's at 11. That's really far that way. Well, that's because that's that carbon that's attached to both of the electronegative atoms. This has been a quick tutorial on NMR and how to use it to piece together entire molecules.